Okay, everybody. Right now is 4:30, and we shall begin our Applied Research Symposium. Okay, hold on. Let me just readjust my screen. No. All right, welcome everybody to the Applied Research Symposium Winter 2026. Now, hosted by CDU Center for Cybersecurity Innovation and School of Technology and Computing, the Applied Research Symposium is designed for students who would like to share their projects, including capstone courses and their internship. The symposium will provide opportunities for students, researchers, and practitioners to discuss the influence and impact of the applied computing on the future of our planet and our society. Now, with us today, our advisors are Dr. Sam, our dean, Michael, uh, who is the advisor for all undergraduate courses, and Dr. Brian May, who is the director for all of the graduate courses. And along with us, we also have Professor T.J. Kim, Professor Siva Kumar, and Professor Thomas Huber. Now, the rooms are assigned as follows, and I'm going to post this link into the chat once again, just so that everybody can follow along and figure it out which section you should go to, just in case, if not already. When you scroll down to the bottom of our website, you should see the sections over here along with the MS Team link to join. And don't worry, because if you are having trouble joining into the room, the student workers will help you coming in by inviting you in. So please scroll down to the bottom of the website, have a look at the schedule, and figure it out where your name is. In some sessions, since there are too many presenters, I cannot assure that all students of the same course will be presenting at the same time. Let's just say that for CS 687, the presenters will be spanned along session 5, 6, and 7. So if you wish to participate in and have a look at all the presenters from this course, then feel free to hop around session 5, 6, and 7. All right. Does anybody have any questions before we begin? Okay, so now, once again, for all presenters, please find your session, and then you may move over to your room respectively. Yes. For those in session 1, please remain and then begin your presentation soon. For all of the guests today or the audiences, you may choose a session which you would like to listen to, and you can hop around whenever you feel like. All right.
Thank you, Harrison. We'll switch over.
Thank you, Harrison. Yeah, thank you.
I'm going to
Thank
give
you,
a minute
Harrison.
for everybody to hop around.
Harrison.
Thank you.
Good luck, everybody.
Mhm.
Okay. Let me do attendance. Parmbir, are you here?
Yeah, I'm right here.
All right. Oscar Burnell, are you here?
Yep, I'm here.
All right, I can see you. And Ahmed Al Kurzorn.
Here.
Okay. Apologies for not spelling your name correctly. If that's the
No, it's
case, I'm not good with the names. That's why. Anyway,
all good.
so Parmbir, you will be going first with your presentation, and the recording starts now.
Okay, share screen.
Yeah, you may share your screen. Let me know if you cannot do it, and then I'll get it fixed for you.
Figuring it out right now. I think I did it.
Yep. Okay. Please begin your presentation. Everybody, turn off your camera and your microphone.
Hello, my name is Parmbir Singh, and today I will be presenting my capstone project titled Enhancing Aerospace Supply Chain Resilience, a predictive and analytics approach to mitigate lead time volatility. This project focuses on how instability in aerospace supply chain can be better understood and addressed using data analytics and predictive modeling techniques. The agenda. I will begin with the problem statement and motivation behind this project, followed by background research and related work. Then I will walk through the approach, system design, and implementation plan. After that, I will cover data collection, preparation, and analysis, including feature engineering. I will then present the key findings, compare my initial assumption with actual results, and walk through the data visualizations. Finally, I will conclude with insights, future work, and references before opening for questions. Abstract. Aerospace supply chains currently face significant challenges due to lead time volatility, which is largely driven by reactive planning and limited supplier visibility. Many traditional models rely on historical averages, which are no longer sufficient in today's dynamic global environment. My proposed solution is a predictive analytic framework that uses data to forecast disruptions before they impact production. The overall goal is to shift from a reactive approach to a proactive data-driven decision-making process. Keywords. These keywords highlight the core focus areas of my project, including predictive analytics, machine learning, and supply chain risk. Together, they represent the intersection of data science and aerospace operations. Problem statement. Aerospace supply chains rely heavily on reactive planning and historical averages. A major issue is limited visibility across multiple supplier tiers, which leads to unpredictable delays. Even small component delays can halt entire aircraft production lines, resulting in significant financial and operational impact. Motivation. The motivation behind this project comes from both industry and academic perspectives. From a business standpoint, even minor disruptions can delay entire aircraft builds. Academically, traditional linear models are becoming outdated due to increasing global complexity. My goal is to develop a scalable solution that turns complex supply chain data into actionable insights. Background. In my research, I reviewed government reports, industry publications, and professional sources. I consistently found evidence of reactive supply chain practices and repeated supplier delays. At the same time, there is a growing shift towards predictive analytics in aerospace. Background evidence reports from organizations like U.S. Government Accountability Office, also known as GAO, and Reuters confirms that limited supplier visibility and capacity constraints are affecting production. Industry leaders are beginning to adopt predictive tools, indicating a shift towards more data driven strategies. The related work, existing research highlights the weaknesses of reactive supply chains, including volatility and delays. It also shows the predictive analytics is emerging as a viable solution. Related work as is state. Currently, aerospace supply chains operate in a reactive manner. This leads to shortages, delayed production schedules, and frequent adjustments by airlines. The related work to be state. The goal is to transition to a predictive system using machine learning and data driven visibility. This allows organizations to anticipate disruptions instead of reacting to them. Related work key takeaways. The key takeaways is that aerospace supply chains are fragile and the root cause is a lack of predictive visibility. The supports this supports the need for an analytic driven transformation. My approach my approach is to develop a predictive analytics framework that detects supplier risks. This involves analyzing historical data, applying machine learning modules, and generating risk scores to support planning decisions. The system design. The system follows a modular pipeline starting with data ingestion and processing. It then moves into predictive modeling and finally outputs risk indicators that can be used for decision making. The implementation plan. The implementation is divided into phases beginning with data preparation and exploratory analysis. Then baseline models are built, followed by machine learning models, and finally development into a dashboard. Technologies I used. I used Databricks for data processing and modeling, Power BI for visualization, and GitHub for version control. These tools allow for scalable and reproducible analysis. The data collection. The data includes supplier delivery data, lead time records, and production metrics. The goal is to identify patterns of volatility and recurring disruptions. My data analysis. This analysis compares aerospace production with supply chain pressure over time. Both variables increase over time, indicating sustained supply chain stress. Data preparation and data bricks. The key takeaway from this analysis is that supply chain pressure appears to be persistent rather than temporary. As pressure increases, production continues to rise, suggesting that manufacturers are operating under ongoing constraints. This indicates that supply chain instability is a structural issue rather than a short-term disruption. Aerospace supply chain dataset 1. This dataset is used to support predictive modeling and risk forecasting. It helps identify how supply chain pressure impacts production outcomes. Here's a picture of the data set. Aerospace supply chain data set 2. The data set created this week's combines three economic indicators that reflect different aspects of the aerospace supply chain. The Aerospace Production Index represents manufacturing output. The Freight Index represents logistics activity. And the Supply Chain Pressure Index captures global disruptions. These datasets were merged into a single monthly dataset that can be used to explore relationships between supply chain pressure and aerospace production performance. Future engineering and next steps. In addition to merging the datasets, I created additional engineered features to better capture supply chain behavior. These include volatility measures such as rolling standard deviation for production and freight, excuse me, as well as changes in supply chain pressure over time. These features allow us to identify periods of instability rather than relying only on raw values. This provides a more accurate view of how disruptions develop within the system. Key findings. The analysis shows that production is increasing, but supply chain pressure is also rising. There is clear volatility in the system and a positive correlation between production and pressure. This indicates that increased production leads to increased strain on the supply chain. My hypothesis versus reality. At the start of this project, I assumed that supply chain disruptions were mostly temporary and caused by isolated events. I also believed that production and supply pressure were only loosely connected and that increasing production would eventually stabilize the system. However, after analyzing the data, I found that these assumptions were not entirely accurate. The data shows that supply chain pressure is persistent rather than temporary, and there is a strong positive relationship between production and supply pressure. In fact, increasing production appears to increase strain on the supply chain rather than reduce it. Additionally, volatility is continuous, indicating a structural issue rather than occasional disruptions. The shift is understanding reinforces the need for predictive analytics to better anticipate and manage these challenges. Data visualization and analysis. So this is the chart that I came up with in Power BI. On the left is the trend analysis, production versus supply chain pressure. The right graph is a volatility analysis, supply pressure change. Bottom correlation analysis, production versus supply pressure. These visualizations provide deeper insight into the data. The first graph shows a steady upward trend in both production and supply pressure. The second graph reveals volatility with frequent fluctuations in pressure over time. The third graph shows a positive correlation between production and supply pressure. Together, these confirm that while production is growing, the supply chain is under increased pressure and unstable stress. This supports the need for predictive analytics to anticipate disruption rather than react to them. So conclusion and future work. In conclusion, this project shows that aerospace supply chain instability is structural rather than temporary, and it intensifies as production increases. This reinforces the need for predictive analytics to shift from reactive response to proactive decision making. With further development, the framework can support more resilient and data-driven supply chain operations. Here's my GitHub. This is the GitHub repository where I track all my project work, including data processing, notebooks, and documentation. These are the key sources used in the research, including academic, industry, and government publications. Thank you for your time, and I'm happy to answer any questions.
Thank you for your presentation. Everybody, do you have any questions for Parambir? Call for one, call for two, call for three. Okay.
Stop
Well,
sharing.
well, since we got some little time left, why don't you, because we're supposed to do Q&A for 5 minutes, but we're not having any questions right now. So would you mind
Okay.
sharing with us the how your project looks like in your GitHub repository, if you have like a running application for it?
So I'd rather talk about the graph itself. Like I don't think I went over it fully.
Yeah, yeah.
If you don't mind,
I wouldn't
okay.
mind.
Yeah. So shoot, I gotta go through the whole. I didn't think about this. Sorry about this. All right. So I kind of ran through it really fast, but like when you click on, the blue circle, this is like it shows the values go from 100, and then you go to the purple, it shows it goes to like 115, and then to like the blue, it shows, it goes to 120. It's like it's showing the production and the supply chain pressure, like how it's rising. Like it's like a downward trend at first, then it goes to like a flat line, and then it goes like upward. So like this is like inconsistent. It's not like proper like how it should, like usually it's like a small slope. It's actually like volatile. So that's what I was like kind of trying to explain. Like overall, okay, let me get off this. Like if you see the graph number 2, like how inconsistent it is, it kind of has some areas where it goes straight, but then it goes jumps up and down. So like that's the supply chain pressure, and explaining like how the aerospace is going up and down as well. Like as you have all these demands with the parts and manufacturing, these will lead to like the mistakes. So like that's what I was kind of getting at.
Yeah. Okay, so that should be all of it, correct?
Yeah, I don't have much more else.
All right. Well, thank you, Prambir, for your presentation. If nobody else have any questions, we're going to move on to the next presenter. Once again, thank you um, for doing a really good job at predictive analysis to mitigate the time mortality.
Thank you. I appreciate it.
Right now, next presenter, Oscar Bernal. You may start sharing your screen and talk about your your capstone project.
All right. Can you hear me?
Yeah.
Okay. Let's
You may
see
start
here.
sharing your screen.
Uh,
Okay, please.
All right.
All right.
Sorry, one moment. Okay. So, hello everyone. My name is Oscar Bernal, and this is my CS497 computing capstone presentation. My project was on exploring the capabilities and limitations of webcam-based computer vision for interactive desktop systems. I'll begin by introducing the problem and motivation behind the project. Then I'll briefly cover the background and related work that informed the study. After that, I'll walk through my approach, design, implementation, and data collection process. Then I'll summarize the data analysis, results, findings, conclusions, future work, and then I'll end with a short pre-recorded demo. So, problem statement. The core problem behind this capstone is that a lot of computer vision systems assume access to better or specialized hardware, such as LiDAR depth sensors or pre-built commercial platforms and infrastructure. In contrast, many home developers, students, and hobbyists would usually only have access to standard hardware, such as home PCs, their laptops, webcams, or the cameras on their smartphones. That raised an important question. What kinds of interactive desktop experiences are actually feasible under these constraints? My project focused on exploring that gap between what computer vision appears capable of in theory and what can realistically be achieved with affordable consumer hardware. My motivation for this project came mostly from a curiosity standpoint. I was interested in computer vision as a field, especially in the context of interactive systems, but I also wanted to better understand what a typical person could realistically build using only their webcam. A lot of online examples of computer vision looked impressive, but they often hid the complexity of the underlying computer vision models or had assumptions about specialized hardware access or involved complex environmental setups. So I wanted to explore where webcam-based computer vision was more easily usable, where it became unreliable, and what that meant for developers trying to prototype interactive desktop tools. Uh, So some background here. Webcam-based computer vision has become more accessible over time because of open source tools, which have made it easier to experiment with real-time visual processing. With the standard webcam, developers can attempt things like gesture control, face tracking, text recognition, and other interaction techniques. At the same time, webcams are limited to 2D RGB input. That means they are especially sensitive to lighting conditions, motion blur, camera placement, cluttered backgrounds, and the distance from the subject. So even though hardware is accessible, the actual performance of these systems vary a lot depending on the computer vision task and the webcam environment. In the literature I researched, I found several recurring themes that I grouped into categories. First, many studies explored gesture-based desktop interaction, such as replacing or augmenting mouse and computer, or sorry, such as replacing or augmenting mouse and keyboard actions with webcam-based input. Some papers used games or web interfaces as controlled test beds for real-time interaction. Other studies looked at human-centric cues, such as face detection, facial landmarks, or gaze-related sensing. Finally, some research used hybrid or multi-modal approaches to compensate for the limits of webcam-only sensing. Overall, the related work showed that webcam-based computer vision can support useful interactions, but usually in constrained conditions or with carefully chosen tasks. My original idea when I was starting this was to compare major open source computer vision libraries broadly across multiple tasks. But during implementation, I realized that this assumption was too simple. because not all libraries support the same computer vision tasks in the same way. So the project shifted into a task-based comparison approach. Instead of assuming feature overlap everywhere, I compared tools only where the tasks were comparable. In practice, that meant comparing OpenCV and MediaPipe for webcam-based face detection and object recognition, and comparing EasyOCR and Tesseract for OCR, object character recognition. The goal of the approach was to collect structured observations around performance, responsiveness, and accuracy rather than trying to claim a perfect benchmark study. The project was designed as a modular Python application so that camera input, task execution, and output logging could be separated cleanly. The idea was to support repeatable testing across multiple tasks while keeping the webcam and runtime conditions as consistent as possible. I organized the project into reusable components for webcam capture, configuration, task adapters, and result logging. And this made it easier to plug in different task pipelines while preserving a common workflow for collecting data. The architecture shown here reflects that flow from webcam input into the task runner, then into outputs such as overlays, logs, and summary files. Implementation turned out to be much more complex than I originally expected. At first, I assumed I could simply load library A, run a task, then load library B, and compare them directly. What I learned or found out during development was that many computer vision tasks do not work out of the box. A lot of them required pre-trained models, additional dependencies, custom adapters, or task-specific setup before I could even get meaningful output. Still, I was able to build a working exploration prototype suite. I implemented live webcam comparisons for face detection, live webcam object recognition, a live webcam OCR, and I also added logging and summary generation so that I could capture output data and compare rough metrics across the tasks. For data collection, I use purposive sampling. That means I intentionally selected test conditions that represented realistic desktop environments and common failure drivers for webcam-based systems. The initial conditions included things like bright and clean environments, more normal or cluttered environments, and dim or farther conditions. For each run, I captured metrics such as FPS, runtime, and detection rate. For each run, I recorded both quantitative and qualitative information. On the quantitative side, I tracked things like total frames processed, average FPS, and processing time. For detection-based tasks, I also tracked how often detections occurred and what labels or outputs were returned. On the qualitative side, I recorded my own observed accuracy and any noticeable issues. This helped because some runs returned detections, but the outputs were clearly wrong or not useful. So the collected metrics were meant to support later analysis, not just raw counting. When I moved into analysis, one of the biggest takeaways was that this project had really become a comparison of working pipelines and not just a comparison of library names. For face detection, OpenCV and MediaPipe could be compared directly. For OCR, EasyOCR and Tesseract could be compared on the same webcam inputs. But for object recognition, the comparison was influenced heavily by which pre-trained models were available and how they were integrated into my project. So the analysis focused less on claiming universal superiority and more on understanding practical trade-offs, implementation difficulty, and where the outputs were reliable enough to support conclusions. The strongest results came from face detection. Once properly configured, MediaPipe performed more smoothly and consistently in real time than the OpenCV baseline I used. Object recognition was much less reliable. I was able to get it working, but the outputs were inconsistent and clearly influenced by the underlying model setup rather than just the library itself. OCR also worked in a rough sense. Both engines struggled under live webcam conditions, especially with a CPU-only execution, small text, and the need to hold text close to the camera. So overall, the project showed that some webcam tasks are very practical, while others quickly expose the limitations of the hardware, models, and implementation pipeline. The biggest finding was that my original assumption was flawed. I had assumed this would be a straightforward comparison of computer vision libraries, but what I learned was that the real comparison was between task pipelines made up of libraries, pre-trained models, setup complexity, and implementation maturity. Second major finding was that MediaPipe was generally stronger for human-centric real-time webcam tasks like face detection. Third finding was that object recognition should really have been framed from the start as a model comparison and not just a library comparison. And finally, live webcam OCR turned out to be much harder to use effectively than I expected, especially under CPU-only conditions. In conclusion, this capstone succeeded as an exploratory project, even though the ending was not what I originally expected. The project showed that webcam-based computer vision is feasible for some interactive desktop tasks, especially face detection, but its usefulness depends heavily on the task, the available model support, and the environmental conditions. It also showed that comparing open source computer vision tools is more complicated than it first appears, because the practical outcome depends on much more than the library name alone. So the main value of this project was gaining a clear understanding of what is practical and what is difficult, and what assumptions future work should avoid. If I continue this project, I would redesign it around model level comparisons rather than library level comparisons. I would also improve the test setup by using more controlled data sets, better lighting, larger printed text for OCR, and more standardized capture conditions. Uh, Beyond that, I became interested in pose estimation, which is another computer vision task, and multi-camera tracking as a future hobby project. I'll now show a short demo of the exploratory prototype tasks. This demo is not meant to represent a polished product, but rather to show the implemented webcam-based comparisons in action and give a sense of the practical strengths and limits I've discussed.
Volume muted on the video.
Yeah, I cannot hear.
Oh, it must not be capturing
The audio.
the audio in the demo, yeah.
Yeah, you
Um,
may set up the audio so then you can.
when you're sharing, you do have the option of say sharing the tab audio or the system audio. You should have ticked it on. You can close down your sharing and then do it again. Screen sharing. You can close it down and do it again.
Oh, okay.
Okay, when you click share, there should be an option down bottom right above the share and cancel button that says also share system audio or tab audio.
Does it include sound?
Yeah.
Okay, let's try it one more time.
Now you should be able to we should be able to hear it.
Okay. Oh, there I am. So you can see here in the terminal, it gives us a bit of information on the testing. The condition for this test will be bright and clean. Right now, I'm not going to set up the way I did for testing, where I would put up a white background. This is just to demonstrate how it functions. There it is. It's because I'm wearing a hat. So the hat sort of obstructs the face detection with OpenCV. MediaPipe is a little bit better at face detection and a little bit more performance. And then we move on to the next vision task, which would be object recognition. It recognizes many different objects, but specifically what I'm wanting it to recognize is the TV in the background, the person in the scene, which is me, and a random bottle that I happen to have on my desk. OpenCV is not doing too good. MediaPipe definitely works. It's not picking up the TV in the background this time, but in my testing it was. And then it sets up, basically goes to the next computer vision task, which is object character recognition. I have a sample note here ripped out from one of my journals to demonstrate with this. There we go. It gets very laggy, but that is the object character recognition. That first run was on Tesseract. This one is on Easy OCR. Easy OCR is incredibly PC intensive. It runs very slowly on the CPU with my setup. Once those have run through, it exports the summary JSON and CSV to our results folder. Every time I run this full cycle test, it essentially adds the data to these tables. All right, and so this concludes my presentation. Thank you all for your time. I'd be happy to take any questions.
Thank you, Oscar. Does anybody have any questions for Oscar?
Quick question, like, so did you use just one kind of webcam, or was it the one that's built on your PC, or to do the demonstrate, to test the different softwares?
I used just my single webcam, the one that's actually right here, this Logitech Brio, which is why I had to pre-record the demo as well, because Windows can't use two webcams at the same time. It would have
Yeah, that makes sense. Yeah. It's pretty neat. I like it. That's nice.
Thank you.
Yeah.
Any other questions? Then I have one question from my end. Have you ever thought of any practical application for webcam-based interactive thingy?
Yes, there's actually many applications in entertainment. A lot of Twitch streamers stream through virtual avatars. So that's one of the big things with it is but that's with pose estimation. And as mentioned earlier, there's also other research papers that developed like gesture based, like you can swipe it to control actions on the computer for like accessibility reasons for people that maybe can't use a keyboard and mouse. In other hardware such as VR technology, there's eye tracking in those hardware that's used for games and other applications as well.
All right. Yeah. Thank you.
Yep.
If we don't have any other questions, we're gonna move on to Ahmad.
Hello.
Yeah. Anyway,
I'll start
thank you,
sharing my
Oscar.
screen.
Yeah, you may
Thank
start
you.
sharing your screen.
Okay. You see my screen. Presentation. You able to see my screen?
You may begin.
Hello, everyone. My name is Ahmed, and today I'll be presenting my capstone project. Is the flow management system, which focuses on improving sprint planning and agile teams. I'll start with the problem and motivation, then I'll cover the background and related work, walk through my system design and implementation, and finish with conclusion work. So the main problem is that agile teams struggle with estimation capacity, visibility, and often overcommit during sprint. And this leads to miss the goal and inconsistent with delivery. So usually like agile is widely used, but there's planning challenge still exists, and team lose productivity and effective overall project success. Sprint planning depends on blocking and team facility and capacity. And if there are aligned planning with becoming under, I'm sorry, it comes with it, and commitment to the team, more work than it can complete. So research shows that structured planning improve outcome and inconsistent with projects. And so other studies shows estimated that often inaccurate and the team is aligned with the capacity with the lead over commitment. So I created with the approach I created that it shows how the guides and the research of the system design started with identify gaps and planning and estimate the then I'm sorry estimation, then design a source system that can support planning analysis in the future. We start with the user, then go with the from front end, back end connections, of course, database layers and analytic models. The system uses full stack architect with JWT authentication and project task data model and the React APIs, and keeps everything source and scalable. On the back end, I added the calibration feature, including share project access with the analytic endpoint to support future insight. For the front end, I use for the data collection, I use the three source of data: research, system testing, and user feedback to focus on usability and collaboration. And I analyzed the pattern form, research, and tested system behavior from the user feedback, and shows the system is easy to use and improving the task. Here are the findings. The key findings are that planning quality affects success. Estimation is still kind of weak, and currently the tool does not fully support planning decision, but that's going to be a future feature. This project also address these gaps by providing source project management, better task visibility, and foundation for future planning analytics. For my future work, next step will include adding sprint level tracking, workflow analytics, dashboards, and more usability testing to improve the system like in the future. And here are the key reference that I used for my research, and I'm gonna go ahead and demo in my local host a project. It's mainly used React.js and started, having front end for the user able to sign in and sign up if there's no account. Have test user for now, so it shows like a dashboard for a project, and these dashboards, they're accessible by each user in the team, and that's in the future also like we're gonna make it like to have it as groups for teams. It's kind of like how GitLab and GitHub does with their issues. Also, you can create projects, and each projects you can create many tasks, and these tasks could be also assigned through the admin, or could be in the future for we add more layers for users if the admin can assign, or any other users can reassign tasks. And this is what I have for now, and I'm happy. Sorry, stop sharing by mistake. Happy to take any questions if you have any question.
Thank you for sharing your project with us, Ahmad.
Okay.
Does anybody have any questions for Ahmad? Call for one. Call for two. Call for three.
I'll stop sharing.
Yeah, you can stop sharing. Okay, everybody. Yeah, then I suppose that is it for today. Thank you,
Thank you.
Harmir, Oscar, and Ahmad for presenting your project with us. And I hope for your success in the future. Yeah.
Thank
I
you.
wish for your success in the
Thanks a
future.
lot.
Thank you.
Okay.
Good day,
This should conclude our the presentation for our applied research symposium today. You may feel free to leave, or moving on to other sessions if they are still presenting, and check out what other students are doing.
Thank you. Have a good day.
Thank you.
Thank
Have a
Good
good
day,
day.
everybody.
Great job, everyone. Have a good rest of your day.
Good rest of your day.